Yeah, why do we usually adopt reinforced concrete column, in construction? Because we have timber. Timber can be used, steel can be used, but why do we oftentimes adopt RC columns? Um, from our calculations, steel has the highest buckling strength among the three, because among the steel itself, RC and timber. But however, RC reinforced concrete columns are adapted in most building projects for several practical and economic reasons. So some of the reasons is what we want to highlight in this video. So first is it is economical. So RC columns are generally more economical than steel columns. The concrete and reinforcement steels are cheaper and more readily available than steel section, which is very, very true, because if you want to compare a steel the size of a column, it's going to be very, very expensive. The second point is fire resistance. Concrete has excellent fire resistance, so RC column can maintain their load bearing capacity for a long time during fire, whereas steel structure requires additional fire protection. So we also see durability. RC columns are highly durable and resistant to corrosion, especially in aggressive environments. So where you have aggressive environments that the weather condition is not friendly, so RC column seems to be suitable. Then steel, on the other hand, is prone to rust and require protection, coating and regular maintenance. So steel requires protection, coating and regular maintenance. Then there's what we call this expansivity in steel, which usually makes it unsuitable for construction purpose, because when there is heat it tends to expand. Then four, we have integration with concrete structure. So RC columns are monolithic with concrete slabs and beam, providing better structural integrity and continuity. This results in improved performance under lateral loads such as wind and earthquake. So all these points, being economical, fire resistance, durability, integration with concrete structure, makes it more suitable than the other steel, RC and timber. So after all these points, you are going to look at the calculations for the steel, the RC and the timber, a calculation comparison to see which is best suitable. Here we are to determine the strength of steel. So we have steel, we have RC column, we have timber. So for us to check the strength, the length, the total length is 3,000 millimeter, which is the same thing as 3 meters. So that's the length of the steel. So the buckling of steel column. So we want to check for the buckling of steel column. So we have the column section, which goes to 150 mm by 150 mm solid steel. You understand? Then we have the length to be 3,000 millimeter. Then both end fixed. So we have the both end of the steel section is fixed, where our K is equals to 0.5. Then modulus of elasticity of steel is 200,000 Newton per millimeter square. So the second thing is to check the moment of inertia of the steel section. The formula for a moment of inertia is I equals to B D cube over 12. So our B is 150 by our D is also 150 divided by 12, right? So which will give us 42.19 multiplied by 10 raised to the power of 6 millimeter raised to the power of 4. So we also check for the effective length of of the steel. So our LE is equals to KL, which is equals to 0.5 multiplied by 3,000 millimeter, which will give you 1,500 millimeter. So that is the effective length. So we check for the buckling. So the buckling load, we'll be using Euler's formula. So we are going to have our PCR equals to pi square ESI over LE that we calculated for square. So if you rough that out, you're going to have PCR equals to 3 kilonewton. That is 37,000 kilonewton. That is for the steel. So we also check for the other one. Yeah, after checking for the strength of the steel, so we also want to check for the strength of RC column to see, at the end of the day, we'll do comparison to see which has greater strength. So you're still making use of the length of 3,000 millimeter, which is equivalent to 3 meters. So, and the column is fixed at both ends. So, and the size of the column is 150 mm by 150 mm. So whereby we're going to use 16 bars, that is 416 and Y16 bars. Then our concrete cover is going to be 25 mm. So, and we know that given column size is 150 by 150 mm, your length is 3,000 millimeter, which is equivalent to 3 meters. Then both end fixed. Then our K is equals to 0.5. Concrete is equals to E, which is equals to 25,000 Newton per meter square. For steel, that is for the reinforcement steel you are introducing to the concrete, our ES is equals to 200,000 Newton per millimeter square. Then we have 4Y16 bars, then we have concrete cover of 25. So the first thing to do is to actually check for the moment of inertia of concrete, so which is IC equals to BD cube over 12. So which is 150 multiplied by 150 cube over 12, which will give you 42.19 multiplied by 10 raised to the power of 6 millimeter raised to the power of 4. So check for the area of one steel. So area of one steel is AS equals to pi into 16 square over 4. That is pi d square over 4. So I know the diameter of the reinforcement is 16. So when you multiply that, you're going to have 201.06 millimeter square. So we also check for distance from centroid to the bar center, which will give us y equals to 75 minus 25 plus 16 over 2, which will give us 75 minus 33, which is equal to 42 mm. So we'll also check for steel distribution to moment of inertia, which is 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 equals to 4 ASY square. So when you multiply that out, you're going to have 1.42 multiplied by 10 raised to the power of 6 millimeter raised to the power of 4. So the next thing is to do transformed gross moment of inertia. So we'll do the gross moment of inertia. We're going to have IT equals to IC plus M minus 1 into bracket IS. So when you rough that out, also you are going to have 52.13 multiplied by 10 raised to the power of 6. So this will now give you a reason to calculate for effective length, which is LC equals to KL multiplied by 0.5 multiplied by 3,000. So we are still going to have 1.5. Then we check for buckling, that is 1.5 millimeter. We check for buckling using Euler's formula, which is going to give you PCR equals to pi square EC IT over LE square. So when you rough that out, you're going to have PCR to be equals to 5720 kilonewton. If you compare it to the first calculation we have, you see that this one is lower. So the strength of RC column is 5720 kilonewton. So we are going to also do for timber, so that we'll be able to compare that of steel, that of this RC column, and that of timber. Yeah, for the strength of timber, we're still going to make use of the length, which is 3,000 millimeter, equivalent to 3 meters, then 150 by 150 millimeters. So these are the parameters that are given. The length, which is close to 3 meters, that we've already said. Then both end is fixed. So we are still considering, in steel we did both end fixed. In RC columns we did both ends fixed. So for timber, we're also using both ends are fixed. So then K is equals to 0.5. Then section of timber column, which is 150 by 150. Then modulus of elasticity, which is E, will be equals to 10,000 Newton per millimeter square. So for the first, we will calculate for moment of inertia, which is I. So our I is equals to BD cube over 12, which is equals to 150 into 150 meter cube. over 12, which will give us 42.19 multiplied by 10 raised to the power of 6 raised to the power of 4. So that is for the moment of inertia. So we look for the effective length, which is LA equals to KL, which is equals to 0.5 multiplied by 3000, which will give us 15 So that is for our effective length. Then we also check for buckling. So the buckling load is PCR, which will give us pi EI over KL all squared. So if you rough that out, you're going to have 1.85 multiplied by 10 raised to the power of 6 Newton. So you convert to kilonewton. So it's going to give you 1850 kilonewton. So the timber column buckling load is apparently 1850 kilonewton. So if you now compared the both for timber and for the concrete and for the steel has the higher strength, but it is very, very expensive. Timber has the lowest strength, you understand, but it might not give you the required strength as compared to concrete. So that is why concrete is most preferable, because it's a composite combination of concrete and steel in construction.